Ladies and gentlemen, please welcome Senior Director of Technology, Pivotal, Cornelia Davis.
Good morning, and thank you for joining us here at SpringOne. Now, 30 years ago or so, when I started my career, programming distributed systems was a little bit niche. There weren't that many people doing it. But then, the internet. We are all distributed systems engineers now. Now, distributed systems, we throw around all sorts of terms that now are relevant to all of us. Things like leader-follower, or eventual consistency, or split brain, or Paxos. All of these different things, and all of those things can lead us to believe that, wow, distributed systems are hard. Or are they? So what we thought we would do this morning is we thought we would talk about a handful of distributed systems algorithms to kind of lift the veil on the mystery. And with that, I'd like to kick things off by introducing two of my colleagues, Therese Stowell and Meaghan Kjelland, to the stage to get us going.
It's really great to be here. Meaghan and I are going to talk about leader-follower. So once upon a time, there was a flock of birds, and they were flying south for the winter to Florida. So everything was going really well. They were taking turns navigating and making steady progress. And then they got to Manhattan, and there's a lot of air traffic, there are tall buildings, and they got separated. And that was a real problem, because if there are two navigators, then they don't get to Florida, they don't get to the same place. But they had a plan. They said, okay, we're going to elect a navigator. The navigator has to have 3 votes, so a majority. And what that means is that if a group gets separated, then they can't elect a navigator. So then when they all come back together again, they can have another election and get to Florida successfully.
Cool. So Cornelia told you that we were going to talk about distributed systems, but so far we've only talked about birds. But leader election is also used in distributed systems as well, in cases where we have identical processes that need some form of coordination. So maybe we have processes that are accessing a shared resource or running different parts of a decomposable problem, and there's no natural choice for a leader because they're all identical. So let's go back to our birds. Instead of a flock now, we're going to call this a cluster, and instead of birds, you're going to have to imagine that these are all virtual machines, and they're running a process accessing a shared resource or something. And we're going to call them nodes or replicas instead of birds. So when E wants to become the leader, E will send a request to the other nodes in the cluster asking if that's okay. If enough of the other birds respond yes, then we say we have a quorum, which means more than half of the nodes in the cluster have agreed on who the leader is. So now we have a quorum because we have 5, and E becomes the leader. So what about the case where the birds get separated? In this case, E was our leader, and now E cannot communicate with the rest of the cluster. This can happen in systems. We call this a network split or network partition, where the nodes within the cluster cannot communicate. And in this case, since E was the leader, this is really bad, right? So the rest of the cluster needs to know that the leader can't communicate with them anymore so that they can elect a new leader. But it's also really important that E knows that it's no longer the leader because it can't talk to a quorum of the nodes in the cluster. One way that some algorithms do this is to have the leader of the cluster always send out a constant reminder that they're the leader. So if the other nodes in the cluster aren't getting that reminder, they know that they need to elect a new leader. And if the leader itself isn't getting responses from a quorum of the nodes, then it knows that it needs to step down as the leader. And that is how our virtual machines got to Florida.
So, thanks. So next up, Mathangi, Venkatesan, and Erin Schnabel will talk about Paxos.
we're going to talk about Paxos. We all know the impact distributed systems have in today's world. What do they primarily achieve? High availability by eliminating a single point of failures. How does this usually happen? Usually there are a replicated set of servers within a cluster. When we have a replicated set of machines, we now have to worry about a consistency problem. How do we maintain data to be consistent across all of these machines within the cluster? This is where Paxos comes into the picture to help us design a consensus module. Considering each of these replicas to be something like a state machine, as long as the order of commands given to each of this replica is exactly the same, we can expect the same output from all of them. Let us look at some of the safety rules that the Paxos protocol imposes. The entire system or the cluster must eventually converge upon one value as the final chosen value. It also has to be made sure that only one value is ever chosen. The single value that is chosen is considered chosen when it has been accepted by a majority of servers within the system. This is what we call as when the cluster has achieved quorum. Paxos does this by making each of the servers within the cluster take up one of the following roles: proposers, acceptors, or learners. Proposers are usually the server machines that accept client requests to execute a command or modify a data. Proposers then make an RPC call by sending messages to the remaining majority of servers within the cluster to accept the message. Acceptors respond to the proposers and actually accept the message, and learners are the observer machines which are interested in knowing what the final chosen value in the cluster is. So Paxos aims to solve a couple of unique problems. How do we make the entire cluster agree upon one value and make sure that multiple values can never be chosen within the cluster? How can this be solved? This is usually done by the implementation of something like a unique proposal number. The proposal number has to be unique across all of the machines in the cluster, so it can be imagined as something like a concatenation of a global sequence number with a unique server ID in the lower order bits. The unique server ID is just to give a uniqueness to the number itself, but the whole proposal number must be able to be ordered. And this is primarily so that the acceptors know that when it receives a proposal, a prepare request, with a proposal number that is lower than what it has seen, it is able to reject this. Paxos proposes a two-phase approach to achieve this. First, the prepare phase, where all the proposer machines, which could be concurrently proposing different values to the acceptor machines in the cluster, send out prepare requests to a majority of servers. At this point in time, it learns two things. One, it finds out if any of the acceptors are already aware of a chosen value, and also establishes a contract where the acceptors now cannot accept or will now have to reject future messages from other proposers that have a lower proposal number. Once the proposers have heard from a majority of the servers, they now send an accept message to all of the acceptors to actually accept the value. Erin will go over more in detail about this. Meanwhile, what could be interesting to us as developers is Cassandra, which is a database we are all familiar with, uses Paxos.
Okay, so this is going to be the Lightning version of what a Paxos instance lifecycle looks like. We're going to do the easy path here. I actually think you should go and look at what some of the Paxos results look like. They're fascinating. So here we have a set. We're not going to show the actual proposers here or the learners. We're just going to focus on the acceptors, and we have 5 because odd numbers are magic. So a proposer is going to propose, I want this value to be X. So it has an ID for that proposal, comes in. It's going to pick a majority. It doesn't even need to know the other two. It's just going to say, I'm going to pick a majority of this 5, and I'm going to tell these 3 people that I want the value to be X. Now, the acceptors say, well, I haven't seen anything better because it's the first thing I saw, so we're good. I'm totally happy with that. Now, another proposer comes in and says, actually, I want the value to be Y. And it's going to pick a majority also, but it happens to pick a different majority. But odd numbers are magic, and so at least one person in the 5 has seen both things. But they're like, dude, that's a better number. So I'm totally fine, and life is wonderful. So they're all going to send back for that prepare response, they're going to say, we're good. Now, the first proposer has no idea that that just happened. So they're going to say, I want you to accept my proposal of X. And S3 has to say, well, sorry, I got a better offer, so I can't give you quorum. We're not going to have X. Proposer 2 comes back and says, can we accept the value of Y? We have quorum. That is the answer for the Paxos instance. You're done at that point. Proposer 1 who didn't know this, even if they come back and propose another value, they're going to get back that the answer is Y. So you're done. So that's the easy path for Paxos. So now we're going to have Cornelia come back, and we're going to talk about how all this stuff fits together again. I can do it. That's good. There you go.
Thank you. All right. So we're talking about distributed systems, so we can't do a distributed systems talk without talking about the CAP theorem. Now, I'll tell you, it's a little bit discomforting to talk about the CAP theorem here today, because tomorrow, in fact, the author of the CAP theorem will be here at SpringOne doing that talk. So it's a little unnerving. But of course, the CAP theorem says that it proved that in a distributed system, you can only have two of these three things: partition tolerance, availability, or consistency. So that means that in a distributed system, you can only have AP, CP, or AC. But the assumption is that it's a distributed system, and we know from the fallacies of distributed computing that the network is reliable, right? That's a fallacy. So we all assume that there's going to be partitions, and so therefore all distributed systems can only be either AP or CP, but certainly not AC. But then Google comes along and publishes this. This is from the Cloud Spanner website, and this is a database that is available in the cloud. It's a distributed system, and if you take a look at the leftmost column here, it sure looks like it says that it's consistent and available, but it's distributed. How can they do this? So let's have a look. You might have heard that Google owns its own fiber. So they're not competing with anybody else's traffic. So they can completely control the fiber. They also get redundancy. So it's not that they have one fiber running, they've got redundant fiber running. So if one fiber is cut, there's still additional fibers that are available. Well, we also know that Google runs millions of servers in production, so they kind of know a little bit about failure boundaries and distributed systems that way. And you put all of these things and more together, and you end up with a system that for much of the time, looks like it's AC. But actually, they can't guarantee that there's never going to be partitions. Yes, they're very rare. So let's take a deeper look at both availability and consistency to see how it's done.
Okay, so this is another lightning round about consistency. We're talking about CAP theorem consistency. And what we mean here is we've got multiple nodes, we want to do the read, and we want to make sure if we do the read at any of those nodes, we get back the most recent write. Now, that requires atomicity and isolation from ACID properties. Now, the most well-known algorithm for atomicity is two-phase commit, which takes your transaction manager and it coordinates around the resource managers, and it makes sure that you can get through prepare and commit, and everybody either did it or they didn't, so you know your data store and everything's great, right? We also know for sure that that doesn't work in a distributed system. Basically, if that tran manager goes away, the entire system comes down in a ball of fiery death, and bad things happen, and many, many papers have been written on how the hell we deal with that problem. So we know that doesn't work. So we talked about Paxos. How many of you have heard about Paxos commit? Oh, a few, that's awesome. So Paxos commit basically says, what happens if we take these resource managers and we put a Paxos instance in place of every resource manager? That means you have a few new guarantees. You know that every resource manager is already independently able to give you an answer all the time of whether or not they can commit or not. And that not answer could be, no, I can't commit, or no, I couldn't figure it out, either of which is definitely a no for doing the commit. So you're officially safe. Atomicity is covered. You're either going to get everybody to do it, or you're going to get nobody to do it. That's great. Now, the one detail here, bringing in leader-follower, is you do have a leader, an elected leader for the transaction, and he just makes sure that we go through the transaction algorithm, because there are transaction semantics that somebody needs to be paying attention to. So, detail about Paxos, if you kind of follow it, is it's async. There's no blocking. No blocking. Which means, okay, so we have it so that we always get an answer, and it's going to be a consistent answer, but we don't know when. So we still don't have cap theorem consistency here, because we don't know that if we do the read, we're going to get the most recent write, because we have absolutely no idea how all this stuff happened. So Google Spanner did a cool thing. Cloud Spanner did a cool thing. They have true time. True time gives them global wall clock time, crazy system of GPS receivers and atomic clocks and time masters and people doing a whole bunch of calculation. But what they get out of that is a notion of global wall clock time with a known bounded period of uncertainty, which means they can wait. So we've got all this Paxos consensus stuff going on, which usually means you're outside of that uncertainty anyway, but because we know what that bound is, when it comes time, we've got consensus from all the resource managers, and we're going to go to do the commit. If there's any uncertainty left in what we think that timestamp has to be, we know exactly how long to wait to make that any uncertainty go away. We now know for sure timestamp order equals commit order. There's your isolation, and you now have effectively two-phase commit in a large-scale distributed system. Ta-da!
Great, thank you. So we're going to talk a little bit more about availability now. So availability in the cap theorem says that when you ask, you will get an answer. And it doesn't guarantee anything about that answer being consistent, but you will get an answer. And so what that means is across these nodes here, a request can go to any one of those nodes and you'll get an answer when you have a request. And the assumption here is, again, that availability, if you've got an available system, that sometimes you'll get stale data. And what we said here is that actually it's an ACID-compliant database. We're not accepting stale data. So how does that work in Cloud Spanner? Well, this is where we left off here with these Paxos-driven writes. So we've got data that exists in a couple of nodes. So what happens now if the query ends up at this node over here in the lower right-hand corner? The data's not there yet. So how does the algorithm work? Well, that node is going to go to the leader. Remember, leader-follower? It's going to go to the leader and say, do I have the latest? It's important that the leader not be responsible for delivering that latest, because that's tight coupling there. Instead, the leader's just responsible for saying, I don't know, the latest is at T of n. And from there, that node on the lower right-hand corner says, I know that I need to wait until I see the data of T of n. Now, independent of that cycle, and that's one of the keys of distributed systems, is that we have a lot of independent autonomous pieces. We have a control loop that's taking care of eventually getting the consistency there. Mathangi talked about it. She mentioned eventual consistency as well. So that control loop is running. Eventually, the data gets there. We know we're now at time T of n, and we can get a response. Now, what happens if that protocol that I just talked about never catches up? Well, another thing that Google Spanner has inside of it is embedded retries. So if I never get back a response, it actually embeds inside of it retries so that it can retry that on some other node. Now, because of the true time and because of owning its own fiber and so on, this eventually consistent model can actually start to look like a synchronous model. And that is pretty darn cool. But the last thing that I want to close on Spanner with is this assumption that I personally had when I first started hearing about and learning about Spanner, and that is that Google Cloud Spanner, its magic is all about true time. It's in that true time API and the atomic clocks and so on. But I want to debunk that assumption as well. It all comes together with this. Google Spanner has multiple nodes, redundancy in the nodes. It has redundancy in the network as well. It also has leader elections, like we saw earlier. Finally, there's a consensus protocol, like we saw with Paxos. It has embedded automatic retries. And finally, it has true time. And it's when you bring all of these things together that the rarity of network, a combination of distributed system patterns, a new novel view of time, that's when you get a globally distributed, highly available, ACID-compliant database. That is the magic of distributed systems. Distributed systems may be hard, but they are wicked cool. Thank you. So I have a confession to make. My 2013 self, so from 4 years ago, sitting out in the audience here today, would have been most surprised in this talk from one thing. I would have been most surprised because it was delivered entirely by women. Thank you. But here's the rest of my confession. That same 2013 self would not even have thought about it if it had been all men. It wouldn't have even registered for me. Yes, Ruth Bader Ginsburg. Ruth Bader Ginsburg, when asked how many women would be enough on the Supreme Court, she said, when there are 9. Right? Now, what I want to point out here is that Justice Ginsburg was not actually saying that we should have a Supreme Court that is only women. What she was doing was challenging our complacency with the status quo, a status quo that allowed the Supreme Court to be entirely made up of men for 192 years before there was the first woman there. Well, I will tell you that my 2017 self is not complacent with that anymore. I'm not satisfied with the status quo. And I invite you to join me and join my co-presenters in not accepting that. Thank you.